Hi everyone, welcome back Team R. So this is your Module 5 demonstration. So this thing's going to get broken up into two videos. So in video 1, which is this one, I'm going to walk through the process for running and interpreting what we're calling random slope models. So last week we learned about how to run an MLM with a random intercept. This week, we're looking at how to go a step further and incorporate models that have a random slope and test whether that's necessary. In part 2, I demonstrate how to run, interpret, and visualize a cross-level interaction. So that's very fun too, and I recommend you check it out. Okay, so let's go ahead and get started. And I'll try to start from a clean slate here. So one way you can do this, and I actually recommend doing this from time to time. So this little broom thing here on the bottom will clear out your R console. And this broom up here will clean out your environment, because notice I have some stuff in my environment, so I want to clear that out. Okay, so now I have my code here, and this is available on Canvas on the website. And again, we're using the leadership data that Garson's using. The reason I'm doing that, we are going to use some other data sets. I know you're probably thinking, oh my gosh, this leadership data again. I think it's nice to learn the fundamentals of MLM, the first few modules, on the same data, so we get used to it, and then we can start to innovate a little bit. So, okay, so let's load in some packages. By now you know our friend Tidyverse very well, and LME4, which is also our multi-level modeling package. So I'm going to run those. And if you notice, I put this little front function here, which is suppress package startup messages. And that's a function you can call. It's from base R. What that does is it eliminates all those little messages that you get when you load up a package like the Tidyverse, which is actually a bunch of packages that are put together. So if you, by now, you know what the Tidyverse is, and you sort of know what it includes. And so I generally don't like to see those messages. So I just put the call to the function right here inside this larger call, which keeps things a little bit simpler. Okay, so we're going to again be using the leadership quarterly data from Gavin and Hoffman, and let's make sure I'm pointed at the right file here. So I'm going to set my working directory to week 4, which is where it should be, and I'm going to load in the leadership quarterly data. Oh, so yeah, you may get this sometimes too. I get this on Macs. For some reason, the working directory doesn't fully translate. So here it thinks that the working directory is week 5 when actually it's week 4. One thing you can do is, instead of running this little line in the actual code chunk, it's some issue with the code chunk, you can run it in the actual R console. So all I did was copy and paste this line here. And you don't need to do this for everything. You just need to do it with loading in the data. So here I ran this in R because for some reason in the console we know that the working directory is here. So if you get that, that's one easy tip. I've discovered that over the years. It can be kind of weird. And then we can glimpse this, and this we can now run in the actual document because we have that data set there. And so this should be all familiar. We have all of our measures. We have row ID, company ID. So these are soldiers nested within company. Then we have our raw items for leadership, task significance, and hostility. And we learned how to calculate alpha scores last week. So you now know how to calculate a scale score and evaluate alpha. And we have our scale scores here, and then our group average scale scores right here. So G lead, G T-sig, and G hostile. So this week, I mentioned this last week, but I just want to show you this week. I want to show you how to actually calculate those cluster level means, because that is a very useful skill. And it also teaches you a really cool function in dplyr, one of the Tidyverse packages, called group by. So this comes up a lot in MLM. So in MLM, oftentimes you have an individual level measure, and you want to take that individual level measure and aggregate it up to the cluster. So you want to take the cluster or group mean. And so last week we did this with the task significance measure. We just looked at it. We didn't actually calculate it, but I want to show you how to actually calculate these things. So it's actually not too bad. So the code chunk down here shows you how to do it. So what I'm going to do is create a new data frame called LQ 2002.1. So that, you could also call it point clean or anything else, right? We're just, again, I don't like touching the original data once I've loaded it in. And we're going to start with LQ 2002. And then, remember, that's what the pipe operator means. And then we're going to group that data by company ID. So what this is going to do is it's going to tell the software, okay, everything that comes after this, all the calculations that come after this, are going to be done by company and not by individual. That's what the group by command does. And you can actually do multiple groupings. Like you could say group by company ID and let's see, like what would be another grouping? Rank, right? If that was something in the Army, or so you can actually use multiple variables to sort of group and split things, which is pretty cool. Okay, so we've grouped by company ID, and then we're going to go to our old friend mutate. Remember, that's the command for creating a new variable based on some function of an old variable. And we're going to create glead, gtsig, and ghostel. Now again, these already exist in the data set, so I'm just showing you how to calculate them. So they should look exactly like these variables up above. So glead is just equal to the mean of lead at the company level. Again, we've grouped by company ID. gtsig is equal to the mean of tsig, and ghostel is equal to the mean of hostel. So we could list some more variables down there if we wanted, so on and so forth. Okay, so then we close parentheses, so that's our mutate function. And then, again, pipe operator, we ungroup the data. So that removes those grouping restrictions on the data. So just to recap, we create a new data set, we group it by company ID, and then we create 3 mean level measures at the company level, and then we ungroup. And at the very bottom, I do a glimpse just to make sure it looks the way it should. Okay, so here's my new variable glead, and the first measure there is 2.882576, and that should be equal to this glead, and it is. And then this one should be equal to this one, and so on and so forth. And notice, these don't change, right? 2.88, 2.88, 2.88, because these people are all in the same company. So it looks like it changes over here. Our first person here is in company number 3. So at some point, this measure is going to change. But for everyone who's in company 2, they all should have the same measure. Same thing for gtsig. That looks the same. And ghostel also looks the same. And of course, you can spot check this as well just by clicking on the data frame, which brings up the view mode. So you can actually kind of scroll around. And so, okay, so company ID changes at person number 25. So if I come over here to my new measures, these things should change at person number 25. So 2.94, so here's where they change. And is that person 25? Yeah, so person 24 to 25. So that looks exactly right, which is great. Okay, so very handy. Group by can really be a useful tool for calculating things. Okay, so now we're going to talk about running random slopes models. So just a little bit of scene setting for you here. When would you do this? Okay, so you would not just jump in, and I mentioned this in the lecture slides, you would not just jump in and say, I'm going to run a model with all random slopes and all predictors. Random slopes, one way to think about this is sort of the icing on the cake, where the cake is the model that you've built, just like we did in the previous week, by adding fixed predictors, not random slopes, but fixed predictors, and testing whether or not those predictors make a good contribution to the model. So when the time comes to test random slopes, you should have a model that you feel pretty good about. This is sort of the last step thing that you check. So the first thing you want to do is to run your preferred model without any random slopes. And getting back to last week, our preferred model was, again, a model that predicted hostility with task significance and leadership as level 1 predictors and group level task significance as a level 2 predictor. So we're actually modeling things at both levels, and we are still predicting hostility, and we have a random intercept here at the company level. Okay, so that's just a recap. So I'm going to run this, and this is a model that we've seen before. So this is not anything new yet, but we always want to start here. And again, I give it a name. I call it model.1 because I'm going to come back to it later. And I can use that for doing model comparisons and all sorts of things. I get my estimates here. So here, T-sig, lead, and GT-sig are all significant. The t-values are well below -2, which is sort of our cutoff at the alpha equals 0.05 level. So we have -0.17, -0.35, and -0.27. These are all continuous variables, which means that a 1 unit change, a 1 unit increase in each one of these is going to predict a decrease of these respective units in our hostility score. Okay, so that's all stuff that we've talked about last week. Now, let's say, okay, so we're really interested in this variable t-sig, task significance. That's the one we're really trying to unpack. So a next logical step, if you're interested in task significance, is to see whether or not task significance should be treated as random as opposed to fixed. So right now, as a fixed effect, we are assuming that task significance, the impact of task significance on hostility, does not change depending on what company you're in. That's what we mean by fixed. However, there are some other possibilities there. It's possible that the impact of that predictor actually differs according to what company you are in, and that's what's called a random slope. And so we can test for this actually pretty easily with the LME4 package in R. So let's add a random slope for t-sig, and we're going to call this model.2. Everything at the front is exactly the same. Notice we have hostile, we have our tilde for our denoting our outcome, and then we have t-sig plus lead plus GT-sig, plus, notice, up above with just a random intercept, our random term is a 1 followed by a pipe operator and then company ID. When we've incorporated a random slope in addition to a random intercept, we just put t-sig in place of 1. That's all it is. So by doing this, we will have a random slope and we will have a random intercept, which is pretty cool. And then we get a summary. So we look at the results here. So we get an interesting warning here. I guess it's maybe I don't know if it's a warning or there's a lower level of kind of like a caution that you get sometimes in R. So there's this message, boundary singular fit. C is singular. So what does this mean? Well, there is a sort of a rule for convergence when you use maximum likelihood. And sometimes when you have a more complicated model, for example, a model that has random slopes, you are not able to get a perfect solution that converges exactly the way that it was designed to. And so this is what you get when you get that kind of a warning. What that means is the software was having trouble estimating one or more of the discrete components, and we can probably guess which one it is, and I'll point it out as we look at it. So is this a good thing? No, it's not great. And unfortunately in R, this does pop up more than in software that you pay for, like Stata. In Stata, the model algorithms that they use are proprietary, and they're sort of designed to be adaptive and try to find a good solution at a particular point. So in this case, we are, basically what we could do is, now what's interesting is these estimates are actually exactly the same as what you get in Stata. So it's interesting. It says it's sort of a questionable fit, but it actually looks just fine. So that's what I recommend. If you have access to other software and you get a message like this, you can always test it somewhere else. But most of the time you're okay. But sometimes you won't even get any estimates at all if the fit is really bad. Not the fit, but if the convergence is really bad. And in that case, you're kind of stuck. You kind of do have to use other software. Okay, so here we have our estimates. And okay, so here's T-sig lead and GT-sig. And those essentially look about the same. They're all negative. They're all in the 0.1 to 0.3 range. But up here, we have a new random effect. So we have a random intercept, and we have a random slope, and we have a random intercept at the a random term at the individual level. So these two elements where it says comp ID, here's our random intercept, and here's its estimate of the variance, and here's our random slope, and here's the estimate of the random variance. And notice that's very small, right? The estimate of the variance is 0.01, and the slope on T-sig is 0.15, minus 0.15. So what that's saying is that could be minus 0.16 in some places. It could be minus 0.14 in some places, but it's not going to vary too dramatically. So it's not a super strong thing to add. Just looking at this, in terms of practical significance, a random slope here is not going to make that much of a big deal. In some cases, it makes a very big deal, which is why we want to test to evaluate this. Okay, so how do we figure out whether or not we should actually keep this random thing? The key for that is this command called rand, which I think we've run before in the context of testing for the ICC and the need for an ICC. So we're going to run rand again, and again I'm using this lazy load convention here. So what I'm calling is the Elmer test package, but I only want to call the random function, the RAND function. So I just say Elmer test and then colon and that one function, and then model.to. Okay, so then first of all we get we get a few estimates here. So these are the single term deletions. So these are the single term deletions. So the first line here, this is the model as we estimated it. So AIC, notice, is 5517, AIC is 5517. So that's our original model. And then this is the model if you deleted the random slope for T-sig. And look what happens. AIC goes up, that's not a good thing. And that results in a change of 20 chi-square points. And that is actually statistically significant. So interestingly, even though it's not really practically significant, this is telling us that the model does improve when we include a random slope for T-sig. So we should probably include it, which is kind of interesting. Okay, so let's do one more example here, or actually a few more examples. So let's try doing the same thing for lead. So should we incorporate a random slope for lead? That is model.3, I'm going to call this. And again, the only difference here is instead of T-sig, I'm going to put lead, and then I'm going to run this. And now here I have a random intercept. I have a random slope for leadership, and I have a level 1 residual. The AIC is 5529. Here are the estimates for my fixed effects. Again, they haven't made a big difference. So, okay, do I want this? Do I want to include this? Maybe is what this is saying, right? So this, here's the model with the random slope for leadership. Here's the model where leadership has been deleted. The difference, notice AIC goes up again. That's not a good sign. It's a difference of about 8 chi-square points, and it's sort of borderline significant. So that might be something that I wanna include if we wanna try that. So you might be wondering, how do you include two random slopes at the same time? It's pretty easy. So I'm going to go back up here to model.3. You just add them right here. So tsig plus lead. So now we have random slopes for both of those. So let me rerun this. So now notice I have a random intercept, I have a random slope for tsig, and I have a random slope for leadership. And they all have variances. And notice over here, when you start to add a bunch of these, you also get estimates of the correlations between those random components. This is why we don't like to dump in a lot of random slopes, because by default, we're actually creating a bunch of covariances between all those random things at the same level. So we're correlating the random slope here with this, the random slope for leadership with the random intercept, and all those things really technically should be estimated to make sure that we have a model that does pretty well. So these models can get pretty complicated. So let's look at if including random slopes for both was a good idea. Well, okay, so this is the model as we ran it with two random components. And it looks like the model gets better pretty significantly when we delete tsig. But it does not get better when we delete leadership. So that's interesting. So this is saying that if you have to choose between the two, leadership's probably better. Actually, no, I just interpreted that backwards. So what this is saying is if you remove tsig, the model gets worse. I'm sorry, the model gets worse because the AIC goes up. If you remove lead, it doesn't make a big difference, and it might actually get a little bit better. So this advice would be telling you if you can only have one, that just including a random slope for tsig is probably the way to go. Okay, so just to recap, in this first part of the video, we talked about adding random slopes, and that is pretty easy to do in R. The key is in place of the 1, like we see in this first model, which is a random intercept, we drop in the name of the variable that we want to have a random slope. So in this case, we added tsig as a random slope, and that seemed to work pretty well. We also tried adding leadership as a random slope, and that worked okay, not as well, but was still significant. And then I just showed you at the very end here how to add two different random slopes at the same time. You just add them both here. And notice, we don't touch the fixed part of the equation. We always include predictors as fixed effects because we need that main part of the estimate. The random component is just the degree to which those estimates might vary according to the cluster. Okay? So in the next part, we're going to talk about modeling a cross-level interaction, which is super fun and hopefully you find useful. Thanks.